Welcome everyone. So we will discuss contest 10 today. So let's look at the results. Pretty good results actually. So people solved. So one person again enslaved. It's always one of students. One of the best of students of this group, I believe. So he solved all the contests before. He solved this contest in 2:51. Pretty close. So we had 3 hours. He had 9 minutes left before solved that problem. Good results. So we'll discuss this solution as well, but all other people did good actually. Maybe I'm not sure why the problem E is not. So we'll discuss problem E. Problem E is tricky. So what I did differently today is in the previous discussions I solved the problems online. So I just discussed the problems and then solved them in online. This time sometimes it was messy because I spent a lot of time trying to figure out how to solve the problem, trying to find the solution, then implementing it, making some bugs, debugging and stuff. So it was kind of messy, and it took. So last week it took like 2.5 hours to solve all the problems because problems was too difficult. Probably maybe I was too stupid last week. I don't know. And also I was not very sure if problems are too difficult or not. So this week I actually solved all the problems before. So this morning I solved all the problems. It took me about an hour to solve all the problems. I did my best not to think about the problems before. So it's not very clean experiment because when I prepared the contest, I kind of read all the problems. So I know what problems I'm giving to you. But I did my best not to think about them. So I really tried to just read the problems, think they're okay, kind of estimate the difficulty, combine this contest, and then not think about these problems. So I hope it was no. So it's not the cleanest experiment possible, but well enough. It's maybe the best I could do. I recorded my solving. So we will just. So the plan for today is just to watch actually me solving all these problems and discuss how I do it and what am I doing at every moment and why I'm doing it. Let's start by looking at this first problem. So in the first problem, I just read the problem statement. It's kind of long. I remember it was something about some cards and stuff, but I didn't think about it a lot. So in this problem, you have some cards. You have some numbers. Numbers are from -x to x. And you're given some cards and you need to add some number of additional cards. So total sum is 0. No, it's pretty straightforward what you need to do. So if you have you already have some cards, you have some sum of these cards, and you want to make this sum equal to 0, you just need to, like from some given point, you move towards the 0. And every time you make a move of at most x, and you need to find the minimal number of moves you need to do to move from this position to 0. And it's just you divide your value by x and round it to the nearest integer above. So you can let me show you how I do it. I'll pause it here. So what do you do? So I read all the all the data. It's easy. So I calculate the sum. I make sure I fit in 32-bit integers because all integers are up to 1,000, n is up to 1,000. So so this sum is up to million, so it will fit in 32-bit integer. No problems here. And here I divide it by x, and you see how I do it here. I divide it by x like this. So I make my number plus x minus 1 divided by x. And this is the easiest way to calculate a number when you want to round up to the closest integer. Yeah. So if you just divide by x, if you don't do this plus x minus 1, you will round it down to, so you make a floor of this division. Yeah. And you want a scale of this division. Yeah. So you want to round it to the closest integer above. You want to find the minimal integer greater or equal than this fraction. Yeah. And the easiest way to calculate it is like this: you add x minus 1, then divide by x. Very nice trick, very useful. You use it everywhere. So every time you want to divide and round up to the closest integer, you do it like this. Easy to remember, easy to use. So let's see. So that's all about the first problem actually. So then I submit it. Oh, so okay. So I calculated, submitted, nothing interesting here. Okay. And now you see how it's interesting how I moved from problem to problem. So I submitted the first problem. I don't wait for the outcome. I just immediately move to the second problem. So that's something I do in every contest. So so when you submit a solution, you move to the next problem, and if you get a wrong answer in the previous submission, you then go back to the previous problem. But at least you spend this time when you wait for the outcome, reading another problem or thinking about another problem. So you don't waste this time, because sometimes if you have in code forces, like you have a lot of participants, waiting queue is big. So sometimes it takes a lot of time just to judge your submission. So sometimes you have a lot of time spent before you have your feedback. So you don't waste this time. You read another problem in this. So I'm reading the second problem. Second problem is pretty straightforward actually. So again, what's described in this problem statement is actually, if you know at least some algorithms, you may figure out that this process described in the second problem looks very much like the normal Euclidean algorithm. So what we do, we have two integers. Every time we subtract the small integer from the big integer. So you have two integers, one of them is bigger, one of them is smaller. So every time you subtract from the largest integer the smallest integer. And that's basically exactly what's happening in the Euclidean algorithm. We do the same thing, but instead we not subtract, we calculate remainder modulo. Yeah? But it's actually, calculating remainder modulo is the same as just subtracting multiple times. Yeah? So what I'm doing here, I know that the number of steps in Euclidean algorithm is small, so I basically implement an Euclidean algorithm. Let me just stop here. So I will test on this. Okay, so what I'm doing here, so I read the data again, and here I'm basically implementing the Euclidean algorithm. It's kind of strange implementation because it happens. Sometimes you have strange implementation in mind, not very canonical implementation of Euclidean algorithm. But what I'm doing here, I have two numbers A and B. I swap them, making A greater than B, just because I can. I don't know. It's not very normal implementation of Euclidean algorithm, but it works. Okay. So now A is the largest integer, B is smallest integer. I divide A by B and get number K. So number K is number of steps you will do when you just subtract B one by one. So I add this number K to my result and subtract K multiplied by B. Here is actually, so this line does the same as just calculating remainder modulo B. Yeah? So I subtract from A number B multiplied by the fraction of A divided by B. So it's normal Euclidean algorithm, just in very strange implemented, let's say. Yeah. So that's it. So I believe it will just work from the first compile. Yes. So it'll just work. So again, the problem may be tricky if you never seen Euclidean algorithm before. If you've seen Euclidean algorithm before, then you kind of notice these similarities. Yeah. So you read the problem statement and think, okay, it looks like the Euclidean algorithm. Maybe I can use something similar here. And then you kind of adopt your Euclidean algorithm to solve the problem you have. Too loud conditioning. Okay, I think it's clear enough. I don't know what else to tell about this problem actually. Let's move to the next problem. Next problem is actually fun. So problem C. So later, after I solve this problem, I actually figure out it can be done easily, but you'll see. So how do I implement this problem? So what we have? We have some structure when we have some stones. Yeah. So we have stones falling from above. I believe I have some picture here. So we have some stones falling from above, and we need to output the final sequence of stuff there. Yeah, so we need to find the order of these stones in the end. So all the stones from 1 to n will fall from above in a line. So in the end, they will stand in some order, and you need to output this order. I have this. I believe I'll just visualize the first example, because just to make sure I understand properly what's happening in this problem. So yes, so I have number 1, then I put in the middle number 2, and number 3, number 4, and I have sequence 3, 5, 4, 2, 1. Yeah, like here. So I do it to make sure I understand the statement properly, correctly. Yeah. So my understanding of this statement is actually the same as the authors intended, because sometimes it may not. Sometimes you misread one word and you understand problem differently, and you solved different problem for an hour, and then you fail. So that's not what you want to do. So sometimes it's good to just to check that your understanding is correct. So you just look at the statement, draw a picture, and make sure that your pictures correspond to the statement. It will not guarantee that you understand properly. So sometimes you have very bad examples, but just very easy examples of just one letter or something like this, because judges do not like you. So sometimes you have bad examples. So any understanding of the problem statement will give you the same result, but not here. So it's here pretty good, pretty solid examples. So if you try, then you're pretty much sure that your understanding is correct. Now, how I solve this problem? So what we need? So we need some data structure basically that allows us to put new element in the middle. Yeah. So we have some sequence of stones, and we need to be able to put new stones in the middle between two existing stones. Yeah. So the way the normal data structure I usually use in this case is linked list, because linked list allows you to put elements in the middle. So if you know two elements and you want to put new element in between, it's very easy to do in linked list. So that's what I did in this problem. I just used linked list to solve this problem. It turns out it can be solved much easier. We will probably look at your submissions and look at them. Just looking where to put numbers 1, 2, and so on, because every time you put element in the end of the existing list, so it may be solved much easier, but I didn't. So because I felt quite comfortable using linked list. Linked list is actually not very popular structure, I would say. So not that many problems are solved using linked list nowadays. But it's easy data structure. So if you see the problem that can be used using linked list, you can just use them. It's easy to implement, easy to debug actually, so you'll see. So what I'm doing, I make array next. So next will show me the next element in the linked list after element. And I make it of size n+1, because I will have one extra element as a dummy element before the first element. So let me show you actually. Do I have whiteboard? Yeah, I'll show you the whiteboard. So you have elements. So every element has link to the next element. Yeah, and sometimes you put new element between some existing elements. Yeah, but sometimes you need to put new elements to the end or to the beginning. Yeah, and if your implementation is not that tricky, so it's like here. So if you don't use any tricks, you need to use some special case when you add new element in the beginning, in the end, and so on. You need to keep track of what is the first element of your list and so on. So what I'm doing instead, I make additional dummy element here as dummy beginning of the list. So so this is just additional virtual element, and in my case it has index 0. So element 0 is a special dummy element. I put it in the beginning. Why I'm doing it? Because it's easy to put new elements here. So now if I want to add new element in the beginning of the list, yeah, I just put this element like I have element before, because you can. It's hard to. It's not really hard, but it's the code is much more tricky if you have this special case when you add elements in the beginning of the list. Yeah, because if the code is different, you need special if. Then you need when you have every if is potential bug, because you have a special case you need to check. Here I don't have any special case, so every time I add new element, I have previous element, so I just need to add new element between these two. So now here, let's move back. So L is my left element. So every time I will add new element after this L. So initially L is 0. So I have only this dummy element. Now, every time I see, if I need to put the left, here I actually made a bug and I misplaced L and R, but it doesn't matter. I will fix it in the end. I put yeah, version. So I'm trying to insert my element in the middle between. Here I add another R because I figure out I actually need 2 pointers to L and R. I actually don't need it. I can calculate R as next of L, but okay, I do it like this. Doesn't matter. So I have 2 pointers from L and R. Let me pause again. So every time I have 2 pointers to L and R, and these are 2 pointers that are borders of my current segment. So I add my new element here. My new element will have index I plus 1 because 0 is a dummy element, so elements from 1 to n. When I add element here, I need to put next here and next here. Yeah. So that's what I will do. I will next L of I plus 1, next of I plus 1 equal to R. And boom. So I moved it out of this if because I do it every time. Now I just decide which way I need to move. So in while if L again L is misplaced, it should be it should be opposite. So in one case I move L to this position I plus 1. In other case I move R to the position I plus 1. Now in the end you just need to iterate over your created linked list, and it's really simple. You just move from 0 every time you move using this array next to the next element. So you will iterate for all elements of your linked list in order. Yes, and here I actually and here I tried the first example. See that the result is not the same, and I'm trying to figure out why. Yes, and I see that I actually the result is the same, but it is reversed. Yeah, so I figured out that I missed letter here. I can just reverse the array in the end. It will also work, but yeah, that's it. So that's it. So this problem C again. Let's actually look at your submission. So let's wait. Yes, okay. So that's what I expected. That's what I expected. So what we can do, we can look at all elements from 1 to n, one by one, and find the position for each element. So to find the position of element 1, you just need to look at the first letter. If first letter is L, you should put element in the end, because 1 will be, all other elements will be to the left from 1. And if first element is R, then you should put 1 in the leftmost position, because all elements will be to the right. Yeah. So you don't need linked list actually, you can just do it like this. But still, that's good. But I still, again, it doesn't matter which approach you take. If it works, it's fine. Okay, so that's how it works in competitive programming. That's what I love about competitive programming. You have a lot of ways to solve problem, but it doesn't matter which way you take. At least as long as it passes all the tests in a given time limit. Let's look problem D. So problem D has long parallel statement. Yes. So what we have in problem D, we have basically we have sequence, some elements okay. So yeah, you have zeros or ones. So 1 means you're awake, 0 means you're asleep, and we can make some segment of size k, or we make it awake. So we make these zeros to ones in some segment of length k. And we need to calculate the sum of elements I of array A corresponding to positions when we are awake. So basically, some elements are deactivated, some elements are activated. What we do, we activate the whole segment and calculate the sum of all activated elements. And we want to calculate this maximal sum of activated elements. Again, if it's first time you see the problem like this, you may be puzzled, but actually what we need to do is to calculate sum, or we calculate segment of length k with maximal sum. Yeah? So some elements are already activated, so we'll just remove them. If the element is not activated, then it has some price basically. So you have some value of this element that will be added to your result if you activate this element. And you just need to find the segment of length k with maximal sum. Yeah? So you will see what I'm doing here. Here I'm reading the data. Yes, here I will just do the following. I will calculate. I will calculate the total sum of all elements. So this is sum of all elements that already activated. Now, if element is not activated, I will put it in array B. So array B will tell me how much I will add to the result if I activate this element. Now the question is just to find segment in array B of size k with maximal total sum. And I will do it using prefix sums. Why not? Prefix sum is the most native way to calculate sums on the segments. So here it can be done easily in this problem, but I normally use prefix sums everywhere when I can use it, because prefix sum is very easy data structure. Again, what I'm doing here, I just calculate this array PS. So this array PS just contains the sums of all prefixes of my initial array. Yeah? Now, when I need to calculate sum on a segment here, I just subtract one prefix sum from another prefix sum, and I get sum on a segment. Now, from all these possible, also you may notice how I do this for loop. So this for loop, I iterate through all segments of length k that lies inside this segment. So I make I plus k is not greater than n. It's one of the way to do it. So I is the left border, I plus k is the right border. So right border should be less or equal than n. That's it. So now I will just calculate the maximum, and I believe that's it. So do we need anything else? I believe not. So again, this is the whole problem. So you read the problem statement, you understand what's going on, then you think, okay, what I need to do? Figure out. You need to find the maximum sum on a segment of length k, and you do it just by using prefix sums, because why not? Easy data structure. Let's move to problem E. So what we have in problem E, we have pretty long problem statement, and that's I believe this the main problem. The main difficulty of this problem is actually to read this whole problem statement and understand what's going on. In this problem statement, they first tell you one problem, and then they ask you to solve a different problem. The initial problem is to find the number of ways to express a given sum using some coins. Yeah? And they ask you to do the reverse problem. So you're given some number of ways, and you need to produce the test where the number of ways to express the given number using the given coins is equal to the given number A. So you're given this number A. And now what I'm reading here, so I'm reading all the problem statement, then I immediately read the constraints, because constraints are the most important part. When people ask you to solve the problem, they should give you the constraints. Yeah. If you don't know the constraints of all the variables, you don't know the size of the arrays, you don't know how many points you have, and so on. You don't know what problem you're actually solving. So these constraints are the most important part of this problem usually. And what I see in this constraint, I see that number A is pretty small. So number A is up to 10 power 5. And numbers in the output are pretty large. So n is maybe up to 10 power 6. So I think, okay, so I need to have some big number n, but the number of ways should be small. Usually it's kind of different. So I expected something different. So usually when you have problems like this, you have number of ways, because number of ways can grow exponentially. Yeah. So normally in problems like this, you have very large number A, number of ways, not number A. So you're given some large number of ways, and you need to produce some small, relatively small example when you have this many number of ways. But in this problem is different. In this problem you have very small number of ways, like 10 power 5. And the test may produce pretty large. So you have m is up to 10. So you have a small number of different coins. But this sum n is maybe pretty large, 10 power 6. This is something not expected. Yeah. So that's why I immediately pay attention to these constraints. And then I think, what I can do? Okay, so what I can do? How can I make the array? How can I make the test when I have exactly this number of ways? And I think about some easy solutions. So I know this problem should be easy, because it's like it shouldn't be that difficult problem. I expected. Yeah. So I'm trying to find some not very complicated solution. No, again, so now I think a lot actually. I believe here we can skip because I just think. Yeah, and here I move to the paper finally. So when I have some idea, again, how to get this idea? That's a tricky question. How do you get ideas? No, you just think. I don't know how thinking happens. So so you upload all this problem to your brain and try to generate some idea, and then you have some decent idea. You actually move to the paper and try to express this idea in some terms. So what I'm doing here, I figure out that if I have situation like this, so if I have just numbers 2 and 1, yeah, what I may do. So if I have some number, yeah, if I have only coins of size 1 and 2, then I can. So the number of ways is just number of coins 2 that I used in this. So all different ways to express this number only differs in number of coins of size 2 I use. I think that maybe why I thought about having only 2 coins, because I thought, what is the easiest possible solution? So you start from something simple. So you think, okay, I need some coins. You think, okay, what is the stupidest coins I may have? Let's start from something simple. If it doesn't work, I would move to some more complicated solution. Yes, but what is the most stupid coin? So you have only 1 coin. So if you have only 1 coin, there's only one way to express your number. So it doesn't work. Yeah. Okay. If I have 1 coin, if I have 2 coins, so what values I may have? So they must have different values. Yeah. So the minimal solution is to use coins 1 and 2. So I think, okay, if I have 2 coins of size 1 and 2, yeah, how can I make the number that has exactly a ways to express this number using coins 1 and 2? And then you see, okay, if you have number 2k, then you may use from 0 to k coins of size 2. Yeah. So number of ways to express this number is k plus 1. And okay, you can do it like this. So now I'll just implement it really fast. Really fast. Okay, how fast can I implement this? Let's see. Okay, here I stop a little. Because I want to write 2 multiplied by a minus 1. Yeah, but then I think if a equals to 1, yeah, then I will have 0. Yeah, because 2 multiplied by 0 will be 0. Yeah. So so I do it plus 1. So I think can I do it this plus 1 or not? I actually can. Yes. Because this number, this number can contain as many coins of size 2 as just number 2a minus 1. 2a minus 1 will also work actually. It will also, so for a equal 1, it will tell me 0, but there is one way to express 0, yes? So, but they don't allow me to make n equal to 0 in this problem statement. You see this, n is at least 1. So that's why I make this plus 1 here. So this number has the same number of ways, but it is positive. Go. So that's it. I'll just I read again all this code, so make sure that I didn't make some stupid bugs, and then just submit it. That's it. That's all about problem E actually. So problem is kind of math problem, so it's maybe math heavy problem. So you need to read statement again, you understand what's going on, and so on. This part is heavy. Implementation is this the whole code. Implementation is easy. So that's it. Let's go to problem F. Problem F, again, it looks similar to many problems I solved before, so that's why I love it. We have some recursive structure. So we have the structure, we have number x. Number x is replaced with x over 2, x mod 2, and x over 2. Then you do the same with both parts, like x over 2. So x mod 2 will never be more than 1. Yeah. So x mod 2, this number in the middle, will be 0 or 1. So we'll not change it. It will stay in place. Yeah. Now, left and right part will be expanded using the same algorithm. Yeah. Let me actually show you. So I didn't do it in in the contest because I can do it without paper, but let's do it now. So what do you so imagine you have some number. So you have some number, let's say 10. Yeah. So you replace it like this. You have number 5 in the left, then number 0 in the middle, and number 5 in the right. Yeah. And after that, you expand both these numbers 5 in using the same process. Yeah. So you put a 5 mod 2 in the middle, and then expand it to 2 and 2, and this also. And this also, so you got 0, you have 1 and 1. In here you have 0, you have 1 and 1. And again, if you solved problems like this before, then you kind of usually see the pattern from here. So what we have some tree-like structure of this process, yeah? But all the subtrees are the same. So what I will do, I will calculate some function, actually function I need, only for different types of subtrees. So I have not that many types of subtrees. Yeah. So I have this small subtrees of 0 and 1. They're just trivial subtrees, let's say. And I have this non-trivial subtrees like 2, 5, and 10. Yeah. And since you have all same subtrees on every level of your tree, you have just log n types of different trees. Yeah. So you have log n types. So what I will do, I will try to calculate something for every type of this tree. Yeah. Now we just need to think what we need to calculate. What we need to calculate. What we need to calculate in this problem is actually number of ones in some segment. In this problem, they have this strange restriction that difference between R and L is no more than 10 power 5. Maybe they expected some solution that rely on these restrictions. So maybe you need to calculate just one by one elements. I did another solution that actually doesn't use this restriction because I can. But maybe you use this restriction and just solve. Maybe you can pick these elements of the final array one by one and do it in log n time every time. Then you have like 10 power 5 multiplied by log. Will also work. My solution just works in log n time without this restriction, but up to you. So let's move back to them, to my code. So okay. So here. So what's my plan? I will. Okay. So first, okay, do it. Okay, here I think why we have this restriction. So what I will do, I will pre-calculate number of, why it's called NZ, I'm not sure. I thought number of zeros, the number of ones. So NZ will be number of ones in a segment of which produced by integer. So for every, move back. So for every number 10, 5, and 2. So for 10. So for 5 and for 2 and for 1 and for 0 actually. I will calculate number of ones I produce in a segment that started with this number. So for number 0 it will be 0, for number 1 it will be 1, for number 2 so it will produce 1, 0, 1, so it has 2 ones. Number 5 has 1, 2, 3, 4, 5 ones. Is it always n? Do I just calculate number n? Yes, I just calculate number n in this problem. Okay, it happens. Okay, now I understand. I didn't do it during the problems because I was too confident that I could solve this problem without it. So so number nz actually equals to number n. Why not? So here I pre-calculate again. What I'm doing is I try to pre-calculate number of ones in a subtree that is generated by number n. I do it like this. Okay, let's speed up a little. So if n is less than 2, it is 0 or 1 will be sent. Here I just pre-calculate number for n divided by 2. Yes, okay, now I look stupid, yes, because yes, I just calculate number of n using this code. Yeah. Okay, and z of n equals to n. Now I know it. Okay. It happens. I'm not embarrassed. Okay. I just try to understand why I have the warning. Okay, so I missed all the warnings. Now here's fun trick. Every time when you need to calculate something in a segment, some number of interesting points on a segment, number of something in a segment, you can reduce your problem to calculate the same on the prefix. Yeah? Okay, the same trick as the prefix sums, but you can do it with any function basically. If you need to calculate some function in a segment, you can calculate it on a prefix and then on another prefix, and then just subtract one prefix from another prefix. Yeah? So here, to simplify the problem, I will calculate function on a prefix. It can be done if you need sum. If you need minimum, it's different. Yeah? Like with Fenwick trees, for example. In Fenwick trees, you do the same trick. Yeah. So Fenwick trees is easy to use when you have sum function. Yeah, because you have sum on one prefix, sum on another prefix, subtract them. You have sum on a segment. When you have something like minimum, you need something like segment tree. Yeah, because segment tree can calculate some function on any segment. Here we need sum. Yeah, not some number of elements. Basically sum. It is sum. Yeah. So I will do it on prefix. So I will do this function that calculates a number of ones on prefix of size r. Yeah. So this function calc will take number n. It is number in the root of my subtree, and number r. It's number of elements I take on the prefix, and it will calculate me number of ones on the prefix of this size. And now I just implement it. So again, if I see what happens if n is less than 2, so it's a special case when you don't make any children, yeah, when you stop. Okay, here I think what is the most elegant way to implement this. I spend some time, I believe. So let's speed up. Here I spend a lot of time figure out how to. Here let's skip it. So here I finally understand that I need to know the length of the segment. Not only number of ones, but also length of the segment. Yeah? So for every segment, I will also calculate its length. Yeah. So again, for every tree, I need to calculate how many elements I produce in the end. And now when I look at it, it's also stupid. Okay. So here I produce of size 1, here I produce of size 3, 3 plus 7 and 15. Okay. Okay, I will also spend a lot of time figure out how to do this. It just closest power of 2, yes. Okay, it doesn't matter. I'm not embarrassed at all. I solved the problem anyways, so okay. So here I calculate the length of the segment produced by the number n. Here just and here I make a box. You can see, so this length n should be equal to length of n minus 1 multiplied. I will fix it later. Yeah. Now what I'm doing, I make recursive function that calculates number of ones on a prefix. When you make recursive function, it's usually easier to start with some edge cases when you stop the recursion. So I stop the recursion when r is less or equal 0, then I don't need to calculate anything. I just stop. If number of elements is greater or equal than number of elements in my segment, then I just take all elements in my segment. Yeah? It's basically the same like you do it in segment trees. Okay, if you don't know how to use segment trees, you can watch my lecture again. Pretty easy. Okay, so these two steps I just borrowed from my normal implementation of segment trees. Yeah, so I stop my recursion when I know the answer. Now in the end, I will just calculate the result when I don't know the answer. Yes, here I think actually too much. I don't know why I'm thinking so long. Yes, here I calculate number of ones in the left part plus here I think too long. So basically what you need to calculate number of ones in the left part, number of ones in the right part on a prefix. Yeah? So we have this prefix. So I calculate number of ones in the left part, number of ones in the right part, and I need to calculate this number in the middle. Yeah. Okay. Why I'm doing it so slow? So here, yes. Okay. So first recursive call, calculate number of ones in the left part. Second recursive call, calculate number of ones in the right part. And only one of this recursive call will be slow, because one of this recursive call will stop because of this, because of one of these cases. Like again, it's like in segment tree. why I'm doing so fast? Because I implemented segment tree couple of hundreds of times, I believe. So I know how to implement segment tree, so I just use all the same tricks like I did in the segment tree. Yes, and here I figure out that I have number 7 instead of 5. So I spend a lot of time debugging this. Let's speed up. So I figured, so I read this, go here, try to debug. Okay, slow. It's very fun to watch yourself when you look clever, but here I'm just look stupid, so I will just keep this. So yeah. So here I finally see. So so again, how I debug it? I basically look at all my variables and check which one is false. So which one is wrong. Yeah. So here I finally figure out that my lengths are calculated wrong. So I go here, find how I calculate these lengths, and find the bug. Yeah. Now it works. So I just submit it. That's it. So this problem F. Tricky problem, yes, tricky problem. But again, how you solve problems like this? You solve by solving a lot of problems like this. So you have some recursive structure which builds you some string, and you need to calculate some statistics on a segment of the string. You basically always do it like this. So you have some recursive function, and just make sure that you calculate the. You just look what you actually need to calculate. Usually you need to calculate something like this, just number of elements, number of good elements. So you can, again, so then you can recursively go and just stop the recursion every time when you know the whole segment. When you need the whole segment, you just pre-calculate the result, like in the segment trees. Okay, I repeat segment tree too much today, but because it's very important data structure. If you don't know how to use segment trees, go to my lecture and learn how to do it. Whew. It's fun. We have so we're half through the contest, and we have just 2 problems left. So I spent half an hour solving 2 other problems. No, let's see. Problem G. Problem G is actually nice. Problem G is actually nice. So it combines some mathematical thinking about some prime numbers. So it's used some, let's say, some number theory. Not really, but again, you need to know at least something about how prime numbers work, and also combine some algorithmic thinking. So you need to figure out what you need to calculate and how you want to calculate. Again, what I'm doing here, I just trying to understand what's going on in this problem, because it's a lot. So usually when I have problem about math, I always at least write the formulas, because I can't do it in my head without paper. So I just write down all these formulas and think what I can do to them. And here I just calculate what will be the denominator of this sum. So I know that the denominator will be x in power a1 plus y2 and so on, like here. Yeah? And I wanna so this number t will be like this, and I want to figure out what is number s, and I just calculate x. Also, okay, so here s is different s. Here s I forgot I have number s here. So this number s just sum of all numbers ai. Yes. So I just see that number. So when I put all the fractions to the same denominator, to this denominator, I will multiply this 1 to some x in power sum of all a's. So s is sum of all ai, yeah? Minus a1. Yeah. So I need this sum. So this will be my denominator, and the denominator will be just x power s. Yes. Now you need to find the greatest common divisor of these two things. And no, it's easy to see the greatest common divisor will be some x in some power, yeah, because in the denominator you have x power s, x is prime, yeah, so only divisors of x power s are all the powers of x, yeah, so the common divisor must be some power of x. So that's easy. Okay, that's kind of trivial. Now we need to okay, the interesting part, we just need to decide which power of x divides the denominator, yeah. So we need to find the maximal power of x which divides the denominator. That's what's problem about. Okay. So again, I just write this formula to find what this problem is about. Yeah. Now I look at the now I'll look at the denominator again. Okay, I misplaced this s minus si to bi because there's just some numbers. Yeah. So I look at this sum. I want to find the maximal power of x that divides all this number. Now I think, okay, if I take the minimal number, let's sort all of them. Yeah. So if I take the minimal power, that all elements of this sequence will be divisible by this minimal power of x. Yeah. Yeah. So all numbers are actually divisible by x in power b1 if I sort array b. Yeah? May I have the larger common divisor? Yeah? So if you so I figured out that all numbers are at least divisible by x power b1. Now I think, is it possible to make all of them divisible by x power b1 plus 1? And I think, okay, it's only possible if I have x elements equal to this minimum. Yeah. So if I have x elements equal to this minimum, then some of these elements will be equal to x power b1 plus 1. Yeah. So I can drop these x elements and replace them with a single element with power of greater by 1. Yeah, okay, when I do this, I actually understand what's going on next. So I'll just apply this operation over and over until I have the final result. Okay, now I just implement it. So as soon as I kind of understand what I plan to implement, I start implementing. Okay, I'm not sure what I will implement actually by this point, but I just start doing it, and on the go I will adjust my plan. Okay, so here I stop, for example. So again I know. I just stop to think a little. Okay, I'll just create array B like before. I create array B, sort it. Okay, so I tried to sort in reverse order because I figured out it will be easier to remove element from the back. So I need to take some minimal elements. Yes, if you have x minimal elements, you can remove them and replace them elements one larger. So I thought I will take some elements from the tail of my array, x elements, and just replace them with a single element. Okay, it's actually possible, but I figured out that it's too hard. So here I check that I have x elements of the same type. Yeah. Yeah. So k minus 1 is the last element. K minus x is x from the end. Yeah. So I checked that the last x elements are the same. But then I thought it's kind of hard to put this new element in the middle. Yeah. It actually would be easier to just replace all minimal elements, yes, and check if they're divisible. But okay, at this point I just rewrote the whole thing. So I thought, what will I do? How will I put this element in the middle? And figure out that it doesn't work. So I just rewrote everything. Yeah. Okay, it happens. So you see, I just erased half of my code and replaced it with another code. Yeah, because I thought my new idea will be easier to implement. So my previous idea also probably worked, but it was kind of hard to implement. So I thought about another idea which is easier to implement and just move to it. So I just to take the new idea, okay, and implement this. So what I will do, I will make a map of counters. So I will count how many powers I have. Then every time I will take the minimal power, so I will take number of elements with minimal power of x and see if this number of elements is divisible by k, by x. Then I will take all of them and replace them with element plus 1. Yeah. So actually I will take element t plus 1. So t is the minimal power of x that I have. If number of elements is divisible by x, I will take all of them and replace them with element t plus 1. Yes, a number of this will be the count of t divided by x. And remove element t completely. So I remove all these elements and add all these elements. If not, just a break. That's it. So now, every time you take all minimal elements, see if number of minimal elements is divisible by x, I remove them all and replace some elements plus 1. Yeah, actually, no, you can stop here. You can do the same trick using arrays. You can do sorted arrays, just the same. But again, it depends on how do you think. So if you think in terms of arrays, implement it using arrays. If you think in terms of maps, you implement using maps. Both solutions have kind of the same time complexity. No, okay, maps will use additional logarithm factor because there is binary search tree, yes, in the map. But it's kind of fast, at least. So it's one solution is linear, other solution is almost linear. So it's n log n, small constant actually. So it doesn't matter which data structure you use vectors or maps. Sometimes it's nice to learn how to use maps, how to use arrays instead of maps. But if you during the contest figure out how to solve using maps, you just implement use maps. When you get time limit, you can move to vectors instead. Probably you don't, yeah. Maps are really actually pretty fast. Yeah, here I try to understand why I have wrong solution, wrong answer. Look at the example, I have 8 and I have 3, and I figure out that you don't need to output the power, so 3 is the power of 2, yes, so you need to output x power 3 actually, yeah. I think too long about this. Okay, and here, yeah. So I just replace it with function here. I'll write my own power because I can. So I'll write function that calculates power of a power b modulo given modulo. Okay, don't write like this. You definitely need to put this to some constant. I believe I was just frustrated at this point because I spent too much time solving this problem. But again, if you're a normal programmer, you would put this this modulo to some constant. Don't do it like this. Usually in normal contest, I have some pre-written code for all the modulo arithmetics, including the binary exponentiation. So I would not write this from scratch. I will just copy it from my library. But okay. I'm not proud of this, but I mean, it works. Okay. Okay, so I just trained how to write binary exponentiation in 1 minute. Okay, and here we try this sum. Here I have wrong answer test 2. It's actually interesting. So at this point, I wrote some. I tested on examples, and I get wrong answer. So what I'm doing next, how I did this. So again, first I read again. I read all the constraints. Make sure I don't have some integer overflow problems. So I check that I have all longs. I don't have any integer overflow problems anywhere. So I just check everything, that I don't have any place when I accidentally multiply two small numbers and so on. So do something what you don't do when you want to calculate. Okay, so I just check that I don't have any simple mistakes. Yeah. So basically, usually the most common mistake is just integer overflow. So I just check all the lines that I don't have any integer overflow problems, don't have any array overflows, they don't have any strange problems. And after that, so after I didn't find any simple mistakes, I actually tried to find some intellectual mistakes. So maybe my algorithm is not good. So I go back here and trying to understand what am I missing? What am I missing? Again, I look at all this problem. Okay, I think a lot actually. So again, I look at this picture for some time, trying to understand, am my solution actually correct? Am I missing something? Is it possible to make probably another power of x greater than I expected? And so on. So I spend a lot of time thinking about this, I believe. Let me see. Yeah. And here I actually figure out what may cause the problem. So I figure out the maximal power I can have in the denominator, but I forgot the denominator has power s. So my result is actually, you need to find the greatest common divisor of numerator and denominator. So it shouldn't be greater than s. And then I think, is it possible to make make a test when you have power of denominator actually greater than power of nominator. And yes, so I'm trying to construct it for some time. Yes, and here I figure out it is possible. It's definitely possible. Yeah? So if you have test of 8 ones, so 8 elements equal to 1, then sum is 8. So in the end you have 7 multiplied by 8. It's too much. Yeah. So yeah. So here I'm actually testing this. Yeah, just so it's a good habit to try. So if you think your solution doesn't work on some special case, just try this special case. No, it's not special, just in some. If you know that example that breaks your solution, just try it. Maybe it's not. Maybe your solution magically works on this example as well because you missed something. Yeah? So I just checked and see. Okay, 1024 is definitely wrong result. Yes, because I have 8 integers, so it should be greater than 256. Yes. So I think, okay, it doesn't work. So I just add this. So I need to get minimum of this and s. Yeah. Because in the denominator I have power s. So it should be greater than s. So I do this, check it. So that's check it now. I pass this test and try again. Normally I would try all the examples also, but I was kind of sure that all the examples will pass because this change will not affect any examples, but probably you do. Probably you should do it normally. Okay, that's it. So that's problem G. Difficult problem, yes, but doable. Okay, let's move to the final problem. Final problem is actually a real problem. You may see problem like this in real contests, and it would be not the easiest problem. So it's really difficult problem. Okay, let's split it into several parts. No, first of all, you need to read this problem statement. It's kind of okay. Sometimes people write problem statements specifically to make you suffer. So there are a lot of strange details in this problem. How they enumerate all the things and so on. But the most strange detail is how they defined which letters you can pick. So you can pick letter if it is in the middle of some palindrome. So that's what's written here. But it should be in the middle of any palindrome. So any palindrome L of length of some positive integer. So it might have length at least 3. So you need to find the number which has like in the center of the palindrome of length at least 3. But it actually means just that two neighboring letters must be the same. So you can pick the number. So that's what I can write in this statement if they don't want to trick you. Just say that you can remove number if two adjacent letters are the same. So that you can remove the letter if two adjacent letters are the same. But instead they write it like this. Just to make you puzzled. So you read this and you need to spend time to understand what's going on. Doesn't change the problem actually. So you're reading this and try to understand what people tell you. Now you think, okay, let's use this. You read. Okay, here I'm just trying to read this and understand. Okay. At some point I will figure out what's happening. Now I read this part, and okay, this part actually looks very similar to what you have usually. So okay, let's stop here. Okay, just by looking at this picture, I have some flashbacks of what I will do next, because okay, if you solved some problem about game theory and grindy functions and so on before, you immediately recognize this picture. Because what's happening here is I'm splitting my game into several independent games. Yeah? So I had one game when I have one big string. When you split this string into parts, then you have several independent games. And when you calculate sum of two independent games, you need to calculate grindy function. So here I already know that I will implement some grindy function stuff. So this problem is about some grindy function stuff definitely. What exactly we will learn later, yeah? But some grindy stuff will happen here. Yeah, let's go. So what I'm doing here. So okay, actually, we'll just read it and just understand what's going on. Okay. Good. So to spend some time reading. Okay, I read too much. Okay. So okay, here I'm just using my paper to think. Yes, okay, it's too much to think in the head. Sometimes I force myself to solve problem without paper, but not here. So here I will actually use some paper because its problem is not that easy. Okay, so here, what I'm doing, I'm trying to see what will happen if I make some move. So if I make some move, so first I mark all the letters that I can take. Yeah? So if I mark all the letters I can take, I see what will happen if I make a move. So if I take this letter, if I take the letter, I will split my sequence into three parts. Middle part is not important because you just have one letter. You cannot do anything with one letter. Yeah. So left and right part are important. So what will happen? You just have all the left part, all the right part, but these two neighboring letters cannot be used. Yeah. So here you can see. So I have this letter and letter to the left immediately cannot be used anymore because you can only use letter if two neighboring letters are the same. But if letters is in the end of the segment, you cannot use it anymore. Yeah. So when you pick one of the let's say active letters, so you have some active letters that you can pick. Yeah. So if you pick some active letter, then neighboring letters become not active. Something like this. So that's what I figure out just by playing with some example. So I draw some example and just play with this. So I try to make some move and see what will happen. What will next player situation will be, yeah, for the next player. Yeah. So situation like this again. You play in some active letter, and when you do it, this letter becomes not active, and two neighboring letters also become not active. And this, I don't know, for me, so this, okay, that give me a strongest flashback from problems I solved before, because there is one of the first problem you solve when you learn how to do all this grindy function and stuff is actually like this. So let me show you. So there is a quite popular problem that you solve first when you learn grindy function. It looks like this. So imagine you have a line again of cells, and you place some tokens. And when you place token, you're not allowed to put tokens in two consecutive. So you place tokens, but you're not allowed to put tokens next to already placed tokens. Yeah? And you make moves one by one, and who will win? And you solve this problem using grindy function. Like you place token, you mark all these points as non-useful. So now you have two independent games. You have independent game, one game here and one game here. So you just calculate grindy function here, calculate max, and you have grindy function of the result. Then you try all possible moves, and just you see the grindy function you can go to, calculate max of all these grindy functions, and you get your grindy function. Again, I will not explain all the grindy function stuff today because it's not the part of this course. Okay, you can watch my lecture about graph games, I believe. In this lecture, I basically tell you what is grindy function, how to calculate it. Here I'll just use it because it's like one of the classical problem about grindy function. Okay, so this is the classical problem when you can place tokens, but you're not allowed to place tokens next to each other. In this problem, we have something similar, but so we place tokens by deactivating some active letter, and we deactivate all neighboring letters also. So it's kind of similar, but it's not uniform. So there are some active letters and some non-active letters. Yeah. So in this problem, I have dynamic program. Basically, you have d of n is a Grandi function for the sequence of size n. Yeah. And you would, so if placed in position I, you have something like I minus 1 n and n minus I minus 2, yes, elements here. So you have some number of elements here, some number of elements here. So you calculate XOR of these two Grandi functions and get the result. So again, your position only defined by the length of the segment. Yeah. Here is something different because I have this it's non-uniform. So I have some letters are active, some letters are non-active. So I plan to do it like this. So I have some segments. So every time my position is some segment of the cells. But then I thought, okay, if I do it like this, how will I recalculate this? So I will recalculate it in linear time. So total time complexity will be n cube. Yeah. So I have n square possible segments. For every segment, I recalculate it in linear time. Yeah. So I have n cube time complexity. It's too much. N is up to like 5,000 if I go correctly. Yeah. Here I go to back to the problem statement and see now length of the string is up to 5,000. So n power 3 is too much. So what I will do instead? I see that actually my initial game can be split into independent games. Yeah. So instead of having this whole array with some inactive letters, I will just say, okay, I just have some sequence of active letters, and every sequence of active letters actually is some independent game. Yeah. So instead of having one big game with some gaps, I have several small games. So I will calculate every sequence of consecutive active letters as a small game. Now I don't have these problems when I have non-uniform structure. Yeah? I can do it like before. I can calculate for any length of the segment the Grandi function in n squared time. And now I just combine these Grandi functions to make the Grandi function of the whole game. Again, so games like this solved usually by dividing your game into several independent games. Yeah. So you have kind of complicated game, but it can be split into independent parts. So you have these independent parts, you calculate Grandi functions of all of them, and then just calculate XOR of them and have Grandi function of your complicated game. So that's what I was looking for. So I was looking for a way to split my problem into some split my game into some independent games. Yeah? And it turns out to be easy because every segment is an independent game. Now I just implement this. So what I need to, okay, here I check, I find all the active letters. Yeah, I check letters active if two neighboring letters are the same. Here I calculate all the segments. No, I do it like this. So this first loop looks for the left border of the segment. So it's left border if it's active and the previous cell is not active. Yeah. If it's active, so I find the left border, then I use another loop to find the right border. Just one way to find all the segments of consecutive active cells. So now I have all these segments. Now I will just implement, let me see. Yeah, here I will just, yes, so here I just calculate the Grandi function. I made bug here, so it must be j here and n must be I. Yeah, I will fix it later. So here again, the plan is to calculate Grandi function for all lengths of the segments. So lengths may be from 0 to n. So I make array of size n plus 1. D of 0 is 0. Yes, for empty segment you lose. So Grandi function is 0. And here I just calculate. Yeah. So for all lengths from 1 to n, yes, I try to calculate the Grandi function. So I make all possible moves. So j is the move. So So I calculate size of the left part, size of the right part. Again, I have a mistake here, I will fix it. Calculate Grandy function of both these parts. Now, G is Grandy function I move to when I make this move. Yeah. Now I mark all the Grandy function I can go to here. And here I find the minimal Grandy function I cannot move to. Yeah? It's just max of all these values. It is my Grandy function. Again, it's just a very classical implementation of this problem. Again, I have some bug here, but it's... Now here I calculate total Grandy function. I combine all these segments. So for every segment I know the Grandy function. Calculate sort of all these Grandy functions. It's my Grandy function. And now I see. If Grandy function is 0, it means I lose. So winner is second. If Grandy function is not 0, then winner is first. Now I also need to output the move. So I look through all these segments, try to make all possible moves. Again, I try to copy this code. Now I actually found this bug. Yes. So I will rewrite. No, not yet. Boom. At some point I will find it. Yes, somewhere here. No. Oh no, it's so I already fixed it. Yeah, so it's I and J. Okay. When I fixed it? It's too far. Oh, how? Okay. When did I fix it? Okay, it's at some point I found it. So this I must be J and this N must be I. Okay. So I actually found when I copied this code. So when you make copy paste, you actually check what code you copy paste. Okay, now I'll just copy this code here. Okay, here I check that if I get my current Grandy function, XOR it with okay, so I take this segment and replace the segment with two small segments. Yeah, if I do this, my new Grandy function will be like this. And I just check it is 0. If it is 0, I can make this move and win. Yeah. Yeah. Okay. Here I found out actually. Yeah. I used this. Oh, okay. It's actually embarrassing, but okay, it's work. Here actually I do something strange, not usually for this type of contest. I actually try to find more examples because I figured these two examples are too stupid. So I try to find at least some non-trivial example because for these two examples it's not very interesting. Yeah. So in this example you have two segments of size 1. Boring. Yes. In this example just don't have any segments. So I try to find at least some segments of size not 1. Again, I'm doing arrays. I'm doing sequences of the same letters because I'm basically want to check that my part that calculates Grandy function for the segment works correctly. Yeah. And here I'm trying a lot. I'm trying to find at least one example which will give me not answer 2. But it always output first and 2. I think maybe I'm doing something wrong. Maybe it's always 2. And then I try to, okay, I'm trying to follow. Okay. And here I stop actually. And I think, okay, what the hell happens? So if in this example, I place token in array. So here I have 3, here you see. So I have 3 active letters in the middle. So if I pick the left one, yeah, so my opponent will pick the 4th one. So if I place 2, my opponent play 4 and win. So this is just wrong answer. Yeah. So again, so just by I was not sure what was the correct answer. I just saw that my answers look suspicious. I dropped some random tests and look at my results look suspicious. Yeah. So when you look suspicious, you look deeper and try to figure out if it's actually correct. Maybe it's just correct. So in this case, this turns to be not correct. Yeah. And now I'll just investigate what's happening. So why? Did you find the bug actually? So I have very simple mistake. So if you found it already, good for you. I did not. Yeah, here. So I run the code and look at the array D and contains all letters equal, all Grandi functions equals to 1. It looks suspicious. It looks suspicious. So I move to part where I calculate my Grandi function here, and figure out that this minimum should be actually maximum. Yeah. But again, I have the same problem. So again, I looked again at my array D. Yep. Now it has different values. Yeah. So now this value calculates correctly. And I thought, what the hell? Why I'm writing the same output when I calculated array D correctly now? So I just checked that I calculated it correctly manually. Yeah. So I must have another bug. When I copy paste this code, be careful when you copy paste the code. When you copy paste the code, you may copy paste the wrong code. Okay? So when you fix the bug, you need to fix it in both parts. Now it's better. First three is actually correct result. So I check again that my samples still work, and then submit. No, that's it. So it will pass the tests. Let's look at your solutions. Okay, how to solve problem H? Okay, so this part is recognizable. Again, do the same thing. Yeah, in this part we just calculate the same dynamic programming. Okay, you do it using one loop. Why not? So you remember where the start, and if you find the end of the segment, you place it in. Oh, why not? No, it's kind of the same solution. Yes. Good. What else to check? Problem F. What's problem F? Ah, this problem. Oh, that's actually interesting. Let's copy this. I want to analyze what's happening here. What the hell what this loop makes? I equals 0. You don't use I anymore. Okay. L is less than R. Okay. S plus equals this. L plus plus here. Okay, I got it. But I was curious because I didn't find anything when you change this L and R, because this for loop, one L is less than R, but you don't change, you change it here. So basically you iterate all elements of this sequence, and here you somehow magically calculate what will be the next digit. Why not? Very smart solution. It's too smart for me. Okay, here's the reason you also iterate all elements. You find some. Okay, so you have this. You have a function to calculate only single elements. So you have this loop. Okay, why not? Problem G. Problem G is not very good. I believe it's kind of the same. No, yes, nothing. Nothing that much funny. Yes, nothing very funny here. Okay, that's it for today. Thank you for coming. See you next week. No, we'll not see you next week. It was the last contest for this year. I will see you in the next year. We'll post a new contest, I believe, in like 3 weeks or something like that. So I'll see you there. So happy new year to everybody. See you next year.